Welcome to our lecture on oceanography. Today we are diving into the fascinating world of ocean temperature. Understanding how the ocean heats up and cools down is crucial because it drives the movement of massive ocean currents, determines where different marine organisms can survive, and heavily influences the climate of our coastal lands. Let's start by looking at where the ocean gets its heat. The primary source of energy for the oceans is, unsurprisingly, the sun's insolation. However, it is not the only source. A small, almost negligible amount of heat comes from the Earth's interior. At great depths, ocean water is heated by volcanism at mid-oceanic ridges, and convection currents circulate this heat upward. Finally, a tiny amount of heat is generated by friction from surface winds and tidal currents.
You might wonder, if sunlight is the main heat source, how do organisms survive at the very bottom of the ocean where it is pitch black? The photic zone, where sunlight penetrates, is only a few hundred meters deep. Below that, there are no photosynthetic primary producers. Instead, bacteria at the seafloor use the heat supplied by the Earth's interior to prepare food. These chemosynthetic bacteria become the primary producers that support a wide-ranging deep-water ecosystem. Just as the ocean gains heat, it must also lose it to maintain a balance. This heat loss happens in three main ways. First, through back radiation, which is long-wave terrestrial radiation emitted from the seawater. Second, through the direct exchange of heat between the sea surface and the atmosphere above it. And third, through evaporation. When water evaporates, it takes away heat in the form of latent heat of evaporation, which the atmosphere then gains. Several factors dictate exactly how temperature is distributed across the oceans. The most obvious is insolation, the daily duration and intensity of sunlight hitting the water. Then we have the rate of heat loss through reflection, scattering, and evaporation. Closely related to this is the ocean's albedo, or its reflectivity, which changes depending on the angle of the sun's rays. A lower angle means more reflection and less heat absorption.
The physical characteristics of the seawater itself also play a huge role. Let's look at salinity. If the salinity of the water increases, its boiling point also increases. Because the water requires more energy to vaporize, the rate of evaporation actually decreases. This means less heat is lost through evaporation in highly saline waters compared to fresher waters.
Underwater topography is another major factor. The presence of submarine ridges and sills acts like a physical wall beneath the surface. These barriers prevent the mixing of waters on opposite sides. For example, the subsurface layers in the Mediterranean Sea have a distinct temperature profile because a submarine sill restricts it from freely mixing with the deeper, colder waters of the Atlantic Ocean. The shape of the ocean, particularly whether a sea is enclosed, drastically affects its temperature. In low latitudes near the equator, enclosed seas record relatively higher temperatures than open oceans because they gain a lot of heat but don't mix with cooler open ocean currents. Conversely, enclosed seas in high latitudes have lower temperatures than open seas because they experience a net heat loss and, again, lack the warming influence of open ocean mixing. We also have to consider the unequal distribution of land and water on Earth. The oceans in the northern hemisphere actually receive more heat because they are in contact with a much larger extent of landmass compared to the southern hemisphere. Additionally, local weather conditions like cyclones act as massive heat engines, transferring vast amounts of thermal energy from the warm ocean surface directly into the atmosphere.
Wind patterns are incredibly powerful drivers of ocean temperature. Prevalent winds generate ocean currents. Offshore winds, which blow from the land out to sea, push warm surface water away from the coast. This allows cold water from the deep to rise up, a process called upwelling. On the flip side, onshore winds blow from the ocean onto the land, piling up warm surface water against the coast and raising the local sea temperature. Finally, ocean currents themselves redistribute heat globally. Warm ocean currents carry tropical heat to higher latitudes, raising the temperature in otherwise cold areas. A classic example is the Gulf Stream, which warms the eastern coast of North America and the western coast of Europe. In contrast, cold currents, like the Labrador Current, bring frigid polar waters southward, significantly lowering temperatures near places like Newfoundland. Now, let's map out how temperature is distributed horizontally across the globe. At the equator, the average temperature of the ocean's surface water is about 27 degrees Celsius. As you move away from the equator towards the poles, the temperature gradually decreases. The general rule of thumb is that the temperature drops by about 0.5 degrees Celsius for every degree of latitude you travel north or south.
There are interesting nuances to this horizontal distribution, particularly in the temperate zones. Here, westerly winds push warm waters from the western side of the oceans over to the eastern side. You might think this makes the eastern side warmer. However, the eastern sections of these oceans are typically dominated by cold currents flowing from the poles. So while the westerlies do warm the eastern sections, they are still not warmer than the western sections.
Let's talk about temperature ranges, starting with the diurnal or daily range. The average daily temperature change in oceans is barely 1 degree Celsius. Why is it so incredibly small? First, water has a very high specific heat, meaning it takes a lot of energy and time to heat up compared to solid land. Second, the ocean is constantly moving. Vertical and horizontal mixing distributes the absorbed heat throughout a massive volume of water, preventing sharp surface temperature spikes.
Because of this slow heating and cooling process, the annual maximum and minimum temperatures of the ocean are delayed compared to land. While land might be hottest in July, the ocean reaches its maximum temperature in August and its minimum in February. This delayed heating is exactly why tropical cyclones, which feed on warm ocean water, mostly occur late in the season, between August and October, or even into November in the North Indian Ocean. The annual range of temperature also differs by hemisphere. The northern Pacific and Atlantic Oceans experience a greater range of temperature than their southern counterparts. This is because the southern hemisphere has vastly more water, which moderates the temperature, and more extensive uninterrupted ocean currents. Additionally, long-term periodic fluctuations occur, such as the 11-year sunspot cycle, which can cause sea temperatures to rise globally. Moving from horizontal to vertical distribution, we look at how temperature changes with depth. The ocean is broadly divided by light penetration. The photic or euphotic zone extends from the surface down to about 200 meters. This layer absorbs almost all the solar insolation, making it the warmest. Below 200 meters lies the aphotic zone, stretching all the way to the ocean floor. This deep zone receives virtually no sunlight, making it significantly colder.
In middle and low latitudes, the ocean's vertical temperature structure is best described as a 3-layer system. The first layer is the top layer of warm oceanic water. It is roughly 500 meters thick, with comfortable temperatures ranging between 20 and 25 degrees Celsius. In tropical regions near the equator, this warm layer is present all year round. However, in the mid-latitudes, it only develops during the warmer summer months. Beneath that warm surface layer lies the second layer, known as the thermocline. This is a critical boundary region that usually begins anywhere from 100 to 400 meters below the surface and is about 500 to 1,000 meters thick. The defining characteristic of the thermocline is a very rapid, steep decrease in temperature as you move deeper. It acts as a transition zone between the sun-warmed surface and the frigid depths. Below the thermocline is the third and final layer, which extends all the way to the deep ocean floor. This layer is incredibly cold, with temperatures approaching 0 degrees Celsius, and the temperature here remains almost completely stagnant, regardless of the season above. It is vast and dark, containing roughly 90% of the total volume of water in the world's oceans. The rate at which temperature decreases with depth changes depending on your latitude. At the equator, because the surface is so warm, the drop in temperature as you go down is dramatic. But in the Arctic and Antarctic circles, the surface water is already close to freezing, largely because ice is a poor conductor of heat. Therefore, the temperature change with depth is very slight. In these polar regions, the 3-layer system doesn't exist. There is just one massive layer of cold water from surface to floor. Water is constantly moving vertically as well. In the cold polar regions, dense, freezing water sinks to the bottom and slowly creeps along the ocean floor towards the equator. Meanwhile, right at the equator, we sometimes see a strange anomaly. Due to massive amounts of heavy rainfall, the very top surface water can actually exhibit lower temperatures and lower salinity than the water just beneath it, temporarily reversing the normal temperature profile. Finally, let's look at a specific example of how submarine barriers affect vertical temperature. At the Strait of Bab el-Mandeb, there is an underwater sill about 366 meters high. This barrier traps water. As a result, the subsurface water inside the strait is incredibly warm, sometimes more than 20 degrees Celsius warmer than the water at the exact same depth just outside the barrier in the open Indian Ocean. This perfectly illustrates how local geography dictates oceanography, a concept we will build on as we explore our next major topic. Let's look at the horizontal distribution of salinity across the globe, starting with high salinity regions. In a normal open ocean, salinity typically ranges between 33 and 37 parts per thousand. However, geography and climate create significant extremes. For instance, in the landlocked Red Sea, salinity reaches as high as 41. The Mediterranean Sea also sees very high levels of 38 or more. In exceptionally hot and dry regions where evaporation is intense, salinity can sometimes spike to 70. Even in vast open oceans, we find regions of high salinity, around 38, that perfectly coincide with high pressure cells. In these areas, there is hardly any rain, and subsiding dry winds cause massive amounts of evaporation, leaving the salts behind.
On the other end of the spectrum, we have low salinity regions. Estuaries are prime examples. An estuary is the enclosed mouth of a river where fresh river water mixes with saline ocean water. Because of this constant mixing, the salinity here fluctuates widely, anywhere from 0 to 35. We see similar fluctuations in the Arctic and Antarctic regions. Here, the salinity varies seasonally, again ranging from 0 to 35. This is primarily driven by the massive influx of fresh water coming from the seasonal melting of the polar ice caps, which dilutes the salt concentration in the surrounding seawater. Focusing specifically on the Atlantic Ocean, the average salinity sits around 36 to 37. But this isn't uniform. In the equatorial region, salinity drops to about 35. Why? Because near the equator we have heavy rainfall, high relative humidity, persistent cloudiness, and the calm air of the doldrums, all of which add fresh water and reduce evaporation. In the polar areas of the Atlantic, salinity is even lower, ranging between 20 and 32, due to very little evaporation and large amounts of fresh water from melting ice. Conversely, the maximum salinity in the Atlantic, around 37, is observed in the mid-latitudes, specifically between 20 to 30 degrees north and 20 to 60 degrees west. These are areas dominated by high pressure cells, meaning clear skies and high evaporation. Moving to the Indian Ocean, the average salinity is slightly lower, at 35. What is fascinating here is the stark contrast between its eastern and western branches. In the Bay of Bengal, we observe a distinct low salinity trend. This is primarily due to the massive influx of fresh river water, most notably from the mighty river Ganga. On the contrary, the Arabian Sea on the western side shows much higher salinity. This region experiences high rates of evaporation and receives a comparatively low influx of fresh water from rivers, leading to a higher concentration of dissolved salts. Marginal seas also show fascinating variations based on their local conditions. The North Sea, despite being located in higher, cooler latitudes, actually records higher salinity. This is because highly saline water is constantly brought in by the North Atlantic Drift. In contrast, the nearby Baltic Sea records very low salinity because it receives large quantities of fresh river water. Further south, the Mediterranean Sea records higher salinity due to intense evaporation in its warm climate. But just next door, the Black Sea has very low salinity because it receives an enormous influx of fresh water from several major European rivers. When we look at inland seas and lakes, the salinity numbers absolutely skyrocket. The salinity of these water bodies is incredibly high because rivers constantly supply them with trace amounts of salt. Since these bodies of water often have no outlet, the water can only leave through evaporation. Over thousands of years, the water evaporates, but the salt is left behind, making them progressively more saline. For instance, the Great Salt Lake in Utah has a salinity of 220. The Dead Sea sits at 238, and Lake Van in Turkey reaches a staggering 330 parts per thousand. Ocean mixing zones also play a role in salinity distribution. On the western parts of the northern hemisphere, we see a distinct decrease in salinity, dropping from 35 down to 31. This specific drop is caused by the influx of melted fresh water flowing southward from the Arctic region. As this cold, fresh polar water meets and mixes with the warmer, saltier waters of the lower latitudes, it dilutes the overall salt concentration in these specific western boundary zones. Salinity doesn't just change horizontally, it changes vertically with depth, though this variation is heavily subject to latitudinal differences and ocean currents. In high latitudes, salinity generally increases as you go deeper. In middle latitudes, it increases up to about 35 meters, and then it actually decreases. At the equator, the subsurface salinity is lower than at the surface. Generally speaking, as you move downward, you will encounter a distinct zone called the halocline. Similar to a thermocline for temperature, the halocline is a layer where salinity increases sharply.
Because high salinity water is denser, it naturally sinks below lower salinity water, leading to a distinct stratification or layering of the ocean. This brings us to a crucial concept, the pycnocline. The pycnocline is a boundary layer separating two liquid layers of different densities. It typically exists at a depth of 100 to 1,000 meters, bridging the large density difference between surface waters and the deep ocean. The pycnocline is formed by rapid changes in either salinity, which we call a halocline, or temperature, known as a thermocline. Because this zone is extremely stable, it acts as a physical barrier, effectively preventing vertical currents and isolating deep water from surface processes. The major exception is in polar regions. Here, the pycnocline is almost absent because the surface water gets so cold and dense that it sinks directly to the bottom, allowing for deep vertical mixing. While winds drive the ocean currents in the upper 100 meters, there is a massive system of currents flowing thousands of meters below the surface. These deep ocean currents are driven entirely by differences in the water's density. Since density is controlled by temperature, or thermo, and salinity, or haline, this process is known as thermohaline circulation and is greatly influenced by the ocean bottom relief, meaning the underwater mountains and valleys shape how these deep currents flow. A critical component of this global conveyor belt is the Atlantic Meridional Overturning Circulation, or AMOC. AMOC is characterized by a northward flow of warm, salty water in the upper layers of the Atlantic and a southward flow of colder, deep waters. Here is how the engine works. As warm water flows northwards in the Atlantic, it cools down. At the same time, evaporation increases its salt content. This combination of low temperature and high salt content drastically raises the density of the water, causing it to sink deep into the ocean near the poles. This cold, dense water then slowly spreads southward along the ocean floor. Eventually, it gets pulled back to the surface in other parts of the world, warms up again, and the circulation loop is complete. Why does AMOC matter so much? First, it is a massive engine for the Earth's heat budget, distributing heat and energy around the globe. For example, Western Europe enjoys a relatively mild climate, even in winter, largely because AMOC brings warm water north via the Gulf Stream and the North Atlantic Drift. Without it, Europe would be freezing. Furthermore, AMOC acts as a massive carbon sink. As the cold water sinks, it pulls dissolved atmospheric carbon down into the deep ocean, storing it for centuries. This carbon sequestration has profound implications for slowing down anthropogenic global warming. However, AMOC is currently a major cause for concern among climatologists. Over the last 150 years, AMOC has undergone exceptional weakening. As the global atmosphere warms, the surface ocean retains more of its heat. More alarmingly, climate change is causing a massive influx of freshwater from melting Greenland ice sheets and the Arctic region. Remember, the whole AMOC engine relies on water becoming salty, dense, and sinking. Fresh water is not as dense as salt water. When this fresh meltwater pours into the North Atlantic, it dilutes the salty water, preventing it from sinking to the bottom. This effectively jams the gears of the entire circulation system. If AMOC continues to substantially weaken, the cascading effects will be severe. First, we would see a decrease in marine productivity in the North Atlantic, because less sinking water means less vertical mixing of vital nutrients. Northern Europe would experience significantly colder weather, losing its warm water heating system. Globally, weather patterns would shift, leading to less summer rainfall in the Sahel region of Africa and South Asia, potentially threatening agriculture. We would likely see a reduced number of tropical cyclones in the Atlantic. Additionally, the changing ocean dynamics would cause an increase in regional sea levels, specifically along the northeast coast of North America. To fully grasp these ocean dynamics, we need to formally define ocean salinity. Salinity is the term used to define the total content of dissolved salts in seawater. It is calculated exactly as the amount of salts, in grams, dissolved in 1,000 grams, or 1 kilogram, of seawater. Because of this ratio, it is usually expressed as parts per thousand, or ppt. Interestingly, a salinity of 24.7 ppt is considered the upper limit to demarcate brackish water, which is saltier than fresh water but not quite ocean water. Salinity is a master variable. It determines the water's compressibility, thermal expansion, temperature, density, and evaporation rates. Ultimately, these physical properties dictate the movement of the sea and the global distribution of fish and marine resources. When we say salt, we aren't just talking about table salt. Seawater is a complex chemical soup. If we look at the dissolved minerals per kilogram of water,
Chlorine is the most abundant, at 18.97 grams, followed by sodium at 10.47 grams. We also find sulfate, magnesium, calcium, and potassium in smaller amounts. When these ions bond, they form various salts. Sodium chloride is by far the most dominant, making up 77.7% of the dissolved salts. This is followed by magnesium chloride at 10.9%, and smaller percentages of magnesium sulfate, calcium sulfate, and potassium sulfate.
So, what ultimately controls the salinity in any given part of the ocean? Salinity, temperature, and density are deeply interrelated. A change in one affects the others. In the surface layer of the oceans, salinity depends mainly on the tug-of-war between evaporation, which concentrates salt, and precipitation, which dilutes it. In coastal regions, salinity is greatly influenced by the fresh water flowing in from rivers. In polar regions, the cycle of freezing and thawing ice dictates salinity. Freezing leaves salt behind in the water, while thawing adds fresh water back in.
To wrap up our discussion, remember that ocean salinity is not uniform. It varies drastically, both horizontally across the globe and vertically with depth, driven by local climates, river inputs, and ice melt. The pycnocline acts as a crucial density barrier between the active surface and the deep ocean. These density differences, dictated by temperature and salinity, drive the massive thermohaline circulation. Finally, the Atlantic meridional overturning circulation is a vital engine for global heat distribution and carbon storage, but it faces a severe threat of slowing down due to modern climate change and melting ice. Understanding these systems is essential for predicting our planet's climate future.